Hi folks, welcome back to Physics with Captain Rod. The reason I'm making this video is to provide you with another example here of how to apply energy principles. So in this example, imagine this kid at the top of a hill in a toboggan, and at the instant shown he's moving 5 meters per second. His buddy Bill here is at the bottom of the hill waiting for him, and we're going to try to calculate the speed of that young man in the sled when he goes past his buddy Bill using energy principles. So first thing we do is we label the two positions we're talking about. So here's position 1, here's position 2. There's already a velocity vector drawn in position 1. I'm going to go ahead and draw one at position 2. So at position 2, this person's moving this way with some speed here that I would call V2, and we're going to go ahead and find it. So when we apply the work energy theorem, we write out PE1 plus KE1 plus work equals PE2 plus KE2, and then we just go through it term by term. Because we're dealing with potential energies, we need to define a datum. The lowest point in the diagram is usually a good place to do that, so I'm going to go ahead and call that my datum. That's where we measure potential energy from. That's going to make PE1 mgh, where the h is equal to this 10 meters here. The KE1 is 1/2 m v1 squared. Right? The work term is 0. I'm going to come back and talk about why it is 0 here in a minute. The PE2 term would be 0 because at position 2, right here, we are at our datum. There's no height. The KE2 term is 1/2 m v2 squared. All right, now I'm going to go back and talk about that work term a little bit. All right, if we drew a free body of the young man as he slides down the hill, if I pick a kind of a random spot, so here's the sled, here's the person. If we start drawing forces on it, we got the gravitational force down. The sled is supported by the hill, right? And that's an example of what we call normal force, which would point this way. If the hill is nice and icy, there'd be no frictional force to worry about or air drag, so I'm going to just assume those away. Now, work terms. In this problem, the gravitational force here does do work by an amount mg times 10 meters. But that's what the potential energy takes into account. So gravity has already been considered if we use a potential energy term. Right? The normal, makes a right angle to the motion of the sled. Right? At this instant, the velocity would point this way. And because the normal makes a right angle to the velocity, it doesn't do any work. So both forces have been considered. The mg is taken into account. The normal's not doing any work. So that's why that work term is 0. Now, glancing this equation over, you'll notice that there's a mass in every term, so it can divide out. So we can write GH plus V1 squared over 2 equals V2 squared over 2. And now it's just a matter of putting in the numbers. So I'm going to put a little NCU here for note consistent units. This is going to be 9.8 times H. Oops, I'm sorry, times 10 meters plus 5 squared over 2 is equal to V squared over 2. All right, a lot of 2's on that right. Keep in mind that that V is V2, so that one there's a subscript. All right, now if we go ahead and calculate this, 9.8 times 10 plus 5 squared over 2, I get 110.5 equals V squared over 2. And then if you multiply by 2 and square root it, I get about 15 meters per second for the speed at the bottom. All right. So I hope that this helps with how to apply this principle, the principle of work and energy. Have a nice day.